Hi everybody, I'm going to try to make a quick video. I know these videos tend to be long. I'm going to try to make them shorter. There's just a lot to say about your second quiz. Now I sent out an email telling you the quiz was open and mentioned that you'll want to be able to find the vertex form of graphs, being able to find the A, find the vertex using formulas, using discriminants, a little bit of complex number work, solving quadratics for application problems, and suggested looking at the applications in section 3.1 and 3.2 for some samples. Hopefully you looked over some of those things. Some of them were stressed in the homework, some of them were stressed a little less in the homework. Like the complex number work, for example, is kind of a background skill. Something that happened a little bit in, I think it was 3.3 when you kind of look through it. But the nice thing is, if your complex number work isn't strong, you now know that and can go check out your complex number work. So hopefully, getting a little bit of heads up was at least a little bit helpful. So the first thing we were asked to do, and again the order might be a little different depending on your particular assignment, but they should all, and the numbers might be a little different because they kind of randomize some of this stuff, but they should be the same basic questions. So, given the function f of x equals x squared minus, I think it's a plus actually, plus 8x minus 21, write it in vertex form, and it even reminds you there what vertex form is. So our goal here is to write this in f of x equals ax minus, h squared plus k form. Now you can do that in two different ways. You can use the negative b over 2a to find your h, plug that in to find your k, and then put it back in this form if you want to do it that way. You can also put it in the form by using completing the square on your formula. So I'm going to do that real quick. F of x equals, there's no lead coefficient, so there's nothing fancy to do. X squared plus 8x. We have to figure out what to add. Figure out what to add to make it a perfect square. Well, with the 8 here, we know perfect squares look like square the first, twice the product, square the last. So this 8 should be twice our other value. So we take that 8, divide it by 2, get the 4, square that 4, we have to add a 16. This is now a perfect square. It will factor as x plus 4 squared. And you can check that if you want. Square the x squared. You'll get a 4x and a 4x when you FOIL. That gives you the 8x. And then 4 times 4, the 16. So good old square the first, twice the product, square the last. Now we can't just add 16 randomly. We'd have to subtract 16 to compensate, or add 16 to the other side and subtract it over later. And then don't forget your minus 21. So the x squared plus 8x plus 16 factors down into x plus 4 quantity squared. And then the minus 16 minus 21 turns into a negative 37. And there's our vertex form. If we're needing to identify the vertex itself, which we are according to our problem, the vertex is the h and the k value. You've got to be careful. Our form is x minus h. So what's being subtracted here? This is x minus a negative 4. So it's negative 4. It's really what makes this thing 0, by the way. A negative 4 would make that 0, so it's the negative 4. And the y value is the negative 37. If you haven't got a lot of experience with completing the square, we have some ways around completing the square, like the vertex formula and the quadratic formula. But being able to complete the square is a skill that will keep coming back. If you need to practice or play with completing the square, be sure to do that. Let's see, our second one here, asked to graph this function using our, asked to graph that function using the graphing utilities. The key to almost all of our graphing utilities is to, Well, one, make sure we understand how the commands for it work. Some of that, when you watched the video, should have helped a little bit on how to enter answers. Also, just a little trial and error can help. But when you graph a parabola, your cursor will put your first point down. As soon as you put that first point down with your cursor, that point is always your vertex. And you'll notice as you move to a second point, it will make that arm and mirror it to another arm. So all you need to know is a vertex and then any other point anywhere on your parabola. So since we want the vertex, we could again use completing the square to put it in vertex form, or if we know our formula, the x value of the vertex is negative b over 2a. It's just like the first term in the quadratic formula. Negative b, or b is negative 4, so the opposite of negative 4 over 2 times 2. So what, 4 over 4? So the x value of our vertex is equal to 1. Now if we want to know the y value of our vertex, we've got to plug that 1 back in. So we need f at 1 to know the y value of the vertex. Of course, in the HK form, the vertex form, you get that k on the end that tells you the y value. But using this formula for the x value of the vertex is nice because we just plug that 1 back in. 2 times 1 squared minus 4 times 1 plus 1 is what? 2 minus 4 plus 1. Negative 2 plus 1 is negative 1. So our vertex is 1, negative 1. So that'll give us where to put our anchor point when we try to graph it. We also need any other point. The nice other point to find is usually the y-intercept. Every y-intercept has an x value of 0. That's why it's a y-intercept, because it's on the x-axis. So if we look back and we look at what happens when the x's are 0, when the x's become 0, the function is 1. So our x-intercept is 0, 1. So when we go to graph this, make sure everybody can see that. When we go to graph this, the vertex we have to graph first using our tool. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So at 1, negative 1, we plant the vertex and then move the cursor up to the 0, 1. We'll draw the arm this way, and it will mirror it to the other arm on the other side and graph us our parabola. Now sometimes you have to be really careful when you use that tool. I have a tendency when I click on points, I'll get it just in the right place. There's usually a little key here that says what your x and y values are. Sometimes when I click it, I kind of push and it moves off. So kind of hover back over it and check, make sure it's where you want it. It can be a little fussy. And also remember there's that little magnifying glass tool up in the corner. If you click on that, it expands the graph, so it's a little bit larger and it's a little bit easier to work with. So, graphing parabola. If you wanted to put it in vertex form, you certainly could. If this is our vertex, your vertex form would have been y equals, or f of x equals 2x minus 1 squared minus 1. So if you, if we put it in vertex form, the 2 is always the a value, the h and k, so a 1 and a negative 1. So if you wanted to use the vertex form, it would have worked just as well. Okay. Number 3 here, use the graph of the quadratic function to write the formula as f of x equals, can you see that? Sorry. Use the graph of the quadratic function f to write its formula as f of x equals a times the quantity x minus h squared plus k. Essentially write it in vertex form based on the picture. So looking at the picture, we need to identify a couple of things. First and foremost, we need to find the vertex. And our vertex there looks like 1, 3. And the nice thing about that is it tells us most of what our vertex form looks like. We'll have f of x equals a. We don't know what that a value is, but then x minus the h1 squared plus 3. So that's most of what our vertex form looks like. We just need to find this a. And that's why I told you on the little notice here, oops, I said, there it is, be sure to know how to find the a. That's this a. To find that a, we need any other point on the quadratic. So look for a nice point. Doesn't matter where it is, really. This is, again, where that zoom helps a tremendous amount. But, you know, let's say we think that point happens to be the point 0, 1. Again, the zooming is really helpful. Or this point here, that's probably a nicer looking one. 2, 0. Because that really looks like it's at 2, 0. So we know that when x is 2, the function is supposed to equal 0. So we put those in. The function is equal 0 when x is equal to 2. And your book and your homework has some examples on these. 2 minus 1 is 1 squared plus 3. So 0 equals a plus 3. So a had better be negative 3. And it should have been negative because this is downward oriented. If we'd have left that a off, it would have been an upward oriented parabola because it would have been positive. So we now know this a is negative 3. So our entire function looks like f of x equals negative 3 x minus 1 squared plus 3. There's a couple things that are coming up in chapter 4. We're remembering that we have a coefficient out in front, and knowing how to find it by plugging in a known value is going to be an important thing later that's easy to miss and easy to miss points on. So be careful about that. Okay, I'm going to try to pick up the pace a little bit here if I can. 1, 2, 3. So this is 4. So I'm just going to kind of start alluding to methodology here. If a football is kicked straight up with initial velocity and a height, then its height above the earth is given by the function. This is, given by that function. That function, we'll highlight that here, that h of t is a function that you will see over and over again. Good old height based on time is negative 16t squared. You'll often see it written as plus v naught, or v sub 0, t plus s naught. And this s naught and v naught stand for initial velocity and initial position. You'll notice you were told in this problem that we started at 96 feet per second. That coefficient there is the initial velocity, the 96 feet per second. From a height of 6 feet plus 6, that's the initial position. Initial velocity, initial position. This 16, by the way, that negative 16 is from the gravity on Earth. So as long as you're on Earth, that's always going to be negative 16. It's half the acceleration of gravity in feet per second, in case you're curious. So this is the height in terms of t. If we're asked to find what is the maximum height reached by the ball, well, this is a negatively facing parabola. So it's got to go, starts at 6 feet, it's got to look like that. And, you throw it upward, it goes upward for a while, gravity eventually takes control, and it goes downward. Max height is right there. Max height is not finding the x-intercepts, so don't plug this into the quadratic formula. Quadratic formula solves for equaling 0. If you were asked to find how long it takes to hit the ground, there you want an x-intercept. By all means, set this equal to 0 and use the quadratic formula. But since we're asked for the max, we want the vertex. So what is the x value, or in this case, the t value of the vertex? Use that negative b over 2a. That will give you when it reaches max height. It'll be a time value. You want to find what that max height actually is, and you're asked what is the actual maximum height the ball reaches. That time value has to go back in for t to find the height at that particular time. You've got to make a distinction between when are you looking for a vertex and when are you looking for an x-intercept. Max height, when it hits the ground. 5, the rectangular field area problem. You will see these area problems a lot. They are, you'll see them on several different tests. They are a metaphor for determining maximum value under restricted resources. Here the restricted resources is fencing, but it can be time, it can be money, it can be work, it can be any number of things. If you have a restricted resource that has to be multiplied by something, then this kind of problem is a metaphor. So again, real quick, we're trying to build a rectangular garden using the side of a barn of one side. So this is a barn that is assumed to be sufficiently large, and you are trying to build a fence. Let's see, the maximum area the farmer can enclose with 100 foot of fencing. So find the dimensions of this and what the actual area is. We don't know the lengths, so give them variables. Say that's an X, that means this is an X, or an L or a W. X is boring, I know. Well, if this is your width, calling it X, and this is your length, that length has to be all 100 feet minus those two X values. If there was a third fence in here for some reason, you're making sub yards, or fencing like in your tomatoes for some reason, then you'd be subtracting 3 X's. If there was another horizontal fence in there, again, because you're subdividing it, then you would divide this into 2, 3, 4 lengths. But if this is your width, your length is your total minus both of those widths. Then the area of any rectangle is width times length. So x times 100 minus 2x. So 100x minus 2x squared is your area. Again, we're trying to maximize that. Maximizing occurs at the vertex. So the x value of your vertex, again, you could complete the square if you wanted to, but you can also use that negative b over 2a. You might get the sense I'm stressing the ability to find vertices. I am. It's going to come up a lot. So the b value, it's the coefficient of the x. These are kind of backwards from standard form, but that's okay. Your b is your coefficient. So negative 100 over 2 times negative 2 is 100 over 4 is 25. So when that's 25, you reach a maximum area. If that's 25, this is 25. If those are both 25, 100 minus 2 times 25, that's got to be 50. Find the max. What is actually the max area? 50 times 25. You need to be able to handle these problems, by the way, when you have extra pieces of fencing in here. So be careful about that. Be prepared for that. But it's just a slight modification of this general idea. So those will come up a lot. They were in your text. You had application problems with quadratics. This is an application of max and mins and quadratics and vertices. We're going to do things like this more complicated as we go along, so we need to be happy and comfortable with it. Okay, number 6 here. Find the equation for the equation shown below. Compute or complete the following. So we want to write the equation in standard form. We want to calculate its discriminant. And we want to solve the equation. This is essentially talking about quadratic formula here. So given 4x squared plus 3x equals 30 minus 16x, first write it in standard form. Essentially means set equal to 0. So 4x squared, add the 16x over, so that'll be plus 19x, subtract the 30 over, set equal to 0. That puts it in our ax squared plus bx plus c equals 0 form. And we generally do want that a to be nice and positive, so having that a nice and positive is helpful. It's actually not entirely necessary, but it is helpful. So then evaluate the discriminant. They actually remind you what the discriminant is. I won't tend to do that, but it's nice to be reminded. Your discriminant is your b squared minus 4ac. That's the part underneath the radical when you're looking at the quadratic formula. It's nice to compute this ahead of time because it does tell you how many solutions you're going to get. So our b is 19, so 19 squared minus 4 times negative 30 is equal to whatever the heck 19 squared is, plus, when you're the negative 4 times the negative 30 is going to give you a positive. Positive what? It's going to be 4 times 120, so that's going to be 480. Nice, cool. 480. So whatever this discriminant is, 19 squared plus 480. If I had my calculator on, I'd throw it out. But it's going to be positive, so we know we're going to have two solutions. One for the plus square root, one for the minus square root. If this is 0, you only have one solution because you're adding and subtracting 0. If this is negative, you have no real solutions. They're all complex numbers because you can't take the square root of a negative. So looking over that discriminant is nice. Be sure you're comfortable with that. Now then, when we go to find our solutions, assuming we have any, a lot of people get discouraged about using this discriminant because they feel like they've wasted time. I've got to go back and solve the thing anyway. Well, if you remember, your quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac. Well, that's where this came from. This discriminant is b squared minus 4ac. So if you know the discriminant just goes under that radical over 2a. So x equals, again, our b is that 19, so negative b, so negative 19 plus or minus the square root of this number. I'm just going to write the 19 squared plus 480 because, again, I don't remember what 19 squared is off the top of my head. Divided by 2 times a. Our a was the 4, so divided by 8. And then simplify if you can. Like if this is a nice perfect square, find that perfect square. If it's not, simplify your radicals. Do all those nice things. But being able to use the quadratic formula comfortably is an important part of many of the things we're going to do in Chapter 4. And remembering the discriminant is a good tool to have in your bag of tricks. Let's see, again, trying to keep this under half an hour if I can. Baseball drop from stadium seat is 89 feet above the ground. Its height S in feet after t seconds is given by this formula. Estimate how long it takes for the ball to strike the ground. Now again, you might recognize that formula, that negative 16t squared is again gravity. This is that same formula. It doesn't have a v naught t because this object, sorry, that's waving around a lot, because this object was dropped, not thrown. So its initial velocity was 0. So there's a little 0t in there that we just don't see. So given our s of t equaling 89 minus 16t squared, again, that's an object falling in gravity, estimate how long it takes for the baseball to strike the ground. Now again, this is a downward facing quadratic starting at 89 feet. But this time, instead of finding where its max height is, it was dropped, so its max height is our vertex here at 89, we'll want to know where it hits the ground. So we actually want to know its y-intercept. Sorry, its x-intercept. So we want to find out where this thing equals 0. So we're going to take that 89 minus 16t squared and set it equal to 0. Anytime you have a quadratic set equal to 0, you certainly have the option of using the quadratic formula, but because we don't have a t term in here, it might actually be nicer to just subtract that 89 to both sides, or add the 16t squared to both sides, divide both sides by the negative 16. T squared is equal to 89 sixteenths. Square root both sides. T is equal to plus or minus. Don't forget that plus or minus. The square root of 89 over 16. We know the square root of 16, we know the square root of 16 is 4. So t equals plus or minus the square root of 89 over square root of 16 is 4. Now, the plus or minus that we get from square rooting both sides, we only really do want the positive one. The negative one comes from the projection of the parabola backwards. But we don't care about that because of this particular application, but always keep in mind it might be there. So how long does it take to hit the ground? Square root of 89/4 seconds. If you want a decimal, round it off. If this was a problem on a test, it's a word problem, so make sure you write a nice sentence as an answer. Now, it would take so many seconds to hit the ground. It doesn't have to be any more complicated than that, but you do need to have that sentence. So again, I want you to kind of highlight that distinction between finding the vertex in the other problem and finding x-intercepts here based on the context of the application. Okay, I could do a whole video on this problem with the rectangles because it's a cool problem. You'll see this a lot, where you have the box or the piece of sheet metal or whatever you've got, and you're cutting out squares. In this particular problem, you're given the size of the squares. They are 5 by 5 all the way across. You're told the original sizes. This side was W, and this was 15 more than that. You were told that the length was 15 more than the width. So if you want to find the volume of the box that you get when you fold those sides up, and there are some examples of this in your textbook. Look through those, read those. Your volume is going to be length, width, and height. So of your new box, that's the bottom of your new box. Your width of your box is this original width minus 5 from each corner, so minus 10. Your width this way is the W plus 5 minus 5 for each corner, so W plus 15 minus 10, so it's going to be W plus 5. The height of this box, well, that's this edge that's being folded up, is height 5. So that's your formula for your volume. So you've got volume equals, and you could multiply this whole thing out, and you will need to be able to do this problem. And you're asked to find if the volume of the box is, 380 inches in this particular problem. What are the dimensions? So the volume has to be 380 equals, simplify that out, it'll be a quadratic. Simplify the quadratic, subtract over the 380, so it's set equal to 0. Use the quadratic formula and solve. Look over the examples of this problem on your text. You will see problems like it again. Again, it's a good metaphor for manipulating limited resources. So it's an important problem for us to know. The last two, real quick, I think I'm going to be about half an hour, are just for complex numbers. So number 9, or whatever order you got them in, the square root of negative 12. We want to simplify that. Well, we know the square root of negative 1 we express as I. So we want to express it in terms of I. But there's more inside here than just that negative 1. We have the square root of negative 1 times 4 times 3. Breaking out that 4 is handy because we know the square root of 4. So we've got the square root of negative 1 times the square root of 4 times the square root of 3. We know all of these except for the square root of 3. The square root of 4 is 2. Square root of negative 1 is I. It's by convention we put the I second, but if you put it first, I'm not going to yell at you. Square root of 3 we can't do anything with because we don't know what the square root of 3 is, and that's our reduced form. If you're rusty with reducing radicals or rusty with your complex numbers, that's okay. The idea here, again, as I mentioned on the last quiz, is to kind of highlight stuff that you might need to look over. If you need to look over more complex number stuff, do so, because again, it's going to come up in chapter 4. The other one's kind of an interesting one. The square root of negative 50 times the square root of negative 2. I think there was one like this on your prerequisite quiz. Again, trying to make sure that material is sinking in because we're going to need it later. It's very common to look at this and go, we have a negative times a negative, so it's a positive. People will often even write that this is the square root of negative 50 times negative 2. Unfortunately, that's not true. The rule that the square root of a times the square root of b is equal to the square root of a times b, that is a truth for a and b such that they're greater than or technically equal to 0. This rule only works for real numbers. It doesn't work for complex numbers. So we're not allowed to just say, oh, those two multiply, it becomes the square root of 100, so it's 10. We have to handle the I. And the nice thing that you can do is just take out that I. Square root of 50 times I times the square root of 2I, where that I is outside the radical. Rearrange this, the square root of 50 times the square root of 2 times I squared. Now that they're positive, we can put them together. Square root of 100, I squared. Square root of 100 is still 10. I squared, as you recall, is negative 1. If you don't recall it, go look it up. So we end up with negative 10, as opposed to positive 10. This can be tricky, sometimes even counterintuitive. But I'll tell you how I like to think about it. This isn't really a full negative 50. This radical essentially breaks it into two pieces. You know, like when you have the square root of 9. The square root of 9 is equal to 3. The radical is breaking that 9 up into two pieces, 3 times 3, two even pieces that multiply together to make 9. Almost like halving it. It's the multiplicative half of 9. That's why we use actually the 1/2 as the exponent, by the way. So when you see something like negative 4's square root, you don't actually have a 4. You only have half of the 4, a 2. You also don't really have this full negative here. You have half of it. So if you take that times, say, the square root of negative 9, okay, the square root of 4 is 2, the square root of 9 is 3, this is giving you half of a negative. We call that I. This is giving you the other half of a negative. We call that I. And we're multiplying them together. 2 times 3 is 6. Those two I parts come together to make a negative 1 times the 6, and we get negative 6. Oops, sorry. So those the two halves of the I of the negative 1's kind of come together to become the full negative 1. So, you know, if you like thinking about that way, great. If you don't, that's okay. But either way, we have to be careful when we have negatives in the radicals and we're multiplying. It can sometimes be a little counterintuitive. So make sure that ends up being negative 10. Okay, that was all of those pieces. Again, I know some of this stuff is highlighted strongly in your homework and some of it's a little bit less so. Again, my goal here is to highlight to you things that you might need to know, might have missed, things that are going to come up really strong later. Somebody mentioned that the quizzes are not worth a tremendous amount of our points. They add up to being about 10%. The whole purpose of that is because this is a way for us to communicate, for you to know what kind of things we need to be focusing on, and for me to kind of know how things are going. Let me know if you liked having this list ahead of time. I can certainly do that. I don't mind doing that at all. And again, if you have any further questions, come by my office, give me a call, send me an email. I love when you guys come by the office. And sorry this was still a little bit long. These quiz videos might just end up being long. Sorry. Hope you have a good day.